Hello, in this video we are going to be performing multiple regression in JMP 12. To do this we are using a dataset called bodyfat.jump, and that dataset is available. The link to it will be available in the YouTube comments, as well as you can get to it by going to my personal webpage, which is also linked to in the bottom of the video. So today we're going to go through the entire multiple regression process in using JMP, and we will walk through this problem. So the data set that you see in front of you is called bodyfat.jump, and what it is it's a data set with 13 variables in it, 12 of them being different types of measurements of a human being that can be used to determine the percentage of body fat that the person has. So for example, some of the columns you can see are age, height, weight, and then various different circumferences of their body. So as you see, neck circumference, chest circumference, abdomen, hip, and so on and so forth. So to get the body fat percentage of a person, one of the ways you can do that is to use this tool called a caliper and look at the circumferences of various parts of their body. Now, I would believe you would agree with me if you had to take 13 different measurements of a person, because that's how many variables there are that are in this data set. It would be very difficult to be able to do all of that, and it would also be a waste of time and resources. So what we want to try to do in multiple regression, in our example, is try to eliminate the variables, which we will call covariates, that really don't have a strong effect on the linear model we're going to build that will be used to forecast somebody or predict somebody's body fat percentage. So you see in this data table we have body fat percent, which is of course going to be our y variable. That's what we're trying to predict. And then you have 13 covariates, again, mostly circumferences of parts of bodies and also the person's age, height, and weight. So we are going to do this by using a specific type of multiple regression process. Now I'll tell you about both of them before we begin. The first type of multiple regression process is called forward substitution. And what forward substitution means is that you start the linear equation that you're building, or the regression equation that you're going to build out of your covariates. You start it with no covariates in it at all. So you just have a y on one side of the equation and nothing on the other side. And then what you do is you start adding step by step one covariate at a time until you reach the optimal equation. And we'll talk later a little bit more about what is the optimal equation. How do you decide that, or how do you find that an equation is optimal? Now, the problem with forward substitution is it works really well if you have just a couple or three covariates, because one of the things we will see is that as we add covariates into the equation, we will find that combinations of covariates are very important. So for example, if you were to put in age, height, and weight as your three covariates, for example, that is very different than putting in age and weight, because height might actually affect both how weight and age behaves in the equation. So it's not just as easy as, adding them in and seeing if that makes a high quality equation. We're going to use the R squared adjusted to determine that. But you have to put them in different permutations and combinations. So again, for two or three covariates, that is totally doable. But if you look at our data set, we have 13 covariates. We would be here forever. So we are going to try or use another different process that is used for multiple regression called backward selection. And backward selection is the opposite of forward substitution. You start with all of the covariates in the regression equation, and then you work your way backward and you try to remove covariates one at a time. So you will see that process being done today, and you will see how we decide what the ideal regression equation is. So first, before we even get started, we do have to remind ourselves that there are assumptions and conditions for multiple regression. in order for us to make sure that that particular analytical method suits our situation. So going back to what you know about regular regression, you know that, first of all, we have to have linear relationships between the variables. It's called the linearity condition. And the only way to check to see if we have linear relationships between y and all of the covariates, so as you see, between body fat percent and age, between body fat percent and height, so between all of your covariates and body fat, the only way we can see if we have a linear relationship is to create a scatter plot of that relationship. So that's going to be the first thing that we're going to do. We're going to create a scatter plot of all 13 XY pairs that we have here. Now to do that in JMP is pretty simple. We're going to go to Analyze, and then we're going to go to Fit Y by X. We're going to take the body fat percent variable and put that in the Y response drop zone. We're then going to take the rest of these covariates, all of the other ones, and I'm going to drag them over to the X factor drop zone. In case you were wondering how I selected all of those covariates at the same time without having to drag over one at a time, just simply highlight the first one on the list, so for example in our case age, and then hold the Shift key on your keyboard and then click the last one. And when you do that, it will highlight all of the values between those two ones that you selected. And a little trick to save you some time. So we have body fat percent in the Y, in the covariates in the X. So let's click OK. So what JMP just did for us is it created 13 scatter plots of bivariate fit scatter plots of body fat percent against all of our covariates. So at this point, you can just look at your scatter plots and determine which XY relationships do not seem to be linear. And some of them are very obvious. For example, if you look at the third one, the bivariate fit of body fat percent by weight of kilograms, that's a pretty linear positive relationship. But some of them are a little bit more vague. If you look at the first one and the second one, for example, body fat percent by age is really kind of all over the place. You may be able to sense a weak linearity to that relationship. And body fat percent by height is almost completely vertical, so that is sure to have a very low relationship. So you can eyeball it, and multiple regression doesn't say that you have to use any particular tool to figure out whether something is linear or not. A lot of times it's quite subjective. Now what I'm using in our example, just as something to make us feel good about whether or not a scatter plot is linear, is I'm going to use the correlation coefficient. Because remember what the correlation coefficient does. It tells us the strength of the linear relationship between two variables. Now, again, that is not part of multiple regression, but I'm using it as a way that we can say, okay, look, anything under a particular correlation coefficient is not suitable, and we're going to say it's not linear. There's not a strong relationship between those two variables. You certainly don't have to use what I'm telling you to use, and in your class that you're taking, you may actually not use that, and it may be completely subjective. So it's up to you, but we're going to use that in this example just for ease of identifying XY pairs that are not linear related. Okay, so the way I'm going to do that is I'm going to go ahead and do a density ellipse command on the scatter plots. Now I'm going to teach you another trick. If you don't want to do that 13 times, which I couldn't understand why you wouldn't want to, the best way to do it is to hold down the control key on your keyboard. If you use an Apple, you hold down the command key. So you hold down control or command, and then you click your red hot spot on one of the graphs, and you go to density ellipse and click on 0.95. And that will draw your density ellipse around all of the densities for all of the scatter plots. So that's what that shift or command key, or sorry, the control or the command key does for you. Now we know the correlation coefficient is buried down here under the bivariate normal area. So I'm going to, again, engage my shift key, or my command key, or my control key, sorry, command or control, and I'm going to click on that arrow. And as you see, it opens all of them up. So now all you have to do is look through and decide, do you have a threshold of your correlation coefficient that you want the relationship to be higher than. So for example, I'm going to say that anything that has a weaker relationship than 0.2 or negative 0.2 is not linear, that I'm not going to include this in this particular analysis. Now, I've done this prior to here quite a few times, and I know, for example, that height, this one right here, is the only one that has a weak correlation coefficient under 0.2. As you see, this one has a correlation coefficient of negative 0.08. If you look through all of the rest of them, I'm just going to spot check a couple of them, but you'll see, for example, this one's 0.6, this one's 0.49, this one is 0.7. So the rest of them, and I would say even if you looked at these subjectively without doing a correlation coefficient, you would agree these were linear. So even this one that looks quite, quite really pushing it when it comes to linearity is still 0.26. Again, this is not a scientific method as far as figuring linearity, but my students like to sometimes have something, a way they can eliminate a variable right away without having to guess. And especially when it comes to an exam situation, I can say, hey, anything under a 0.2 for a correlation coefficient, take that out right away because it's not linear or it's not a good enough relationship. So that's what we did. Okay, so right now we only have one covariate that we're not going to even include in the multiple regression equation. So that's the height. Okay, we're not going to include that in our model when we go to build that. So that's all you need to do so far. So we've now removed one of the covariates already, and we haven't even done the multiple regression. So I'm going to minimize this this plot window in case we may need it later on. Who knows? Now what I'm going to do is actually start the multiple regression. So to do that, I'm going to go to the Analyze menu, and then I'm going to go to Fit Model. Okay. And what I'm going to do is, it's a pretty easy setup. You're going to take your Y variable, in our case, body fat %, and drag that to the Y drop zone. And then you're going to take all of the covariates of your interest. Now remember, we're doing backward selection, so we're going to use all of the covariates to begin with, except for height, because we've already decided that that's not a linear relationship. So I am going to, again, use my wonderful shift trick, and then I'm going to unclick height using the control or command trick. So you get good at using those shift and control keys. And I'm going to drag those down to where it says construct model effects down here on the bottom. So that's all I've had to do so far. In the upper right-hand corner of this window, change the emphasis drop-down to minimal report, and then click Keep Dialog Open. That will allow this window to stay open and set up so that we can continue to perform this process. Because remember, this is backward selection. We're going to have to do this lots of different times. So we don't want to have to keep setting this window up every single time we do it. All right, so our window is set up the way we want it to be. The body fat % is in Y. The covariates of interest are in the construct model effects window at the bottom. We have emphasis set to minimal report, and we've clicked the Keep Dialog Open button. Okay, so we're going to go ahead and click Run. And you will right away, I'm going to move some windows out of the way here, you will right away have a report window. And now there's a lot of information on here. So I'm going to kind of walk you through it slowly to be able to figure out, to arrive at the final regression equation. So here's basically what we're going to do. We're going to be paying attention really to two areas of this output window. If you scroll down in your output window, we're going to be paying attention to two major areas. The first is up here where it says Summary of Fit, and we are going to be paying attention to this R-square ADJ, and that's the adjusted R-square. And if you remember what that is, remember, first of all, R-square is just the percentage of variation that's accounted for in your current model. So whatever linear model you're dealing with, it's what percentage of the variation in your data was accounted for by that model. The difference between R-square and R-square adjusted is R-square adjusted, or adjusted R-square, contains a penalty for there being multiple variables in the regression equation. So that's why it's a little bit lower. You notice the R-square is 0.748 and the R-square adjusted is 0.735. So we're going to be looking at the R-square adjusted because we're doing multiple regression. So we want that penalty. So It's the same measurement though, however. It's the percentage of variation accounted for by the model in your data. So that's the first thing we're going to be watching, and you'll see how we'll watch that in just one second. And then at the bottom here where it says parameter estimates, we are going to be paying attention to this last column. And you'll notice this last column, which is labeled probability greater than absolute value of t. Okay, these are your p-values for a t-test. Now you're wondering, what does a t-test have to do with this? Well, every single one of these covariates, age, weight, thigh circumference, wrist circumference, you name it, every single one of these covariates actually have a hypothesis test linked to them, unbeknownst to you. So, as you know, hypothesis tests have a null and an alternative hypothesis. So every one of these covariates has the following null and alternative hypothesis. The null hypothesis is that this covariate is not significant to the regression model. The alternative is this covariate is significant to the regression model. Okay? So what your goal is in order to prove that a covariate is significant to the regression model, well, then you have to reject the null hypothesis, because the null hypothesis is that it's not significant to the regression model. So if we're using our standard alpha level of 0.05, then you really want all of these p-values in the last column to be below 0.05. And whichever covariates you're left with, they must be significant to the regression model. Now there's a problem. You can't just come in here and say, well, there's 1, 2, 3, 4, 5, 6, 7 covariates right now that are above 0.05. So let's just get rid of them and we're done. And unfortunately, it doesn't work that way. And here's why it doesn't. There are variables or covariates in this list that depend on each other. They actually are important to each other, and if one of them is missing or changes, another one tends to respond. We call this collinearity. I'll give you an unrelated example. So let's say you're trying to determine the price of your home and how much it's worth so you can sell it. Now, if I'm a real estate agent and all you tell me about your home is how many bedrooms it has, and you say, my home has 6 bedrooms. I say, wow, that's great. That's a lot of bedrooms and your house is probably worth quite a lot of money. But if you go ahead and then tell me, oh, one other thing, my house also is only 1,500 square feet. Well, then I start thinking, wow, those are some small bedrooms. And so because you introduced that second covariate or that second variable into the equation, I know that the number of bedrooms means a higher home value when it's by itself. But when it's coupled with another covariate, such as the square footage of the home, well, then the price of the house now really depends on not only the number of bedrooms, but as well as how large it is. So that is called collinearity, when one variable affects the equation in one way, and then when you add another variable, it affects the equation in another way, or it has a different effect. So you will not be surprised that when we start removing covariates from our equation using backward selection, you will notice that p-values in this column will change as we remove them. So that's why you simply cannot just remove all of the ones below 0.05 and be done, because we have to account for collinearity. So you'll notice we'll take ones out, we'll take covariates out, and you'll notice that sometimes there are other p-values that dip below 0.05 when previously they were not. And then sometimes you will notice there are ones that were below 0.05 that go above 0.05 that previously weren't. So you're really going to have to do this the right way, one covariate at a time. So I'm going to tell you how to do that now. So you're going to start with the highest p-value, because obviously that's the biggest offender. The ones with the highest p-values are very far away, and they are doing the worst amount of damage as far as failing to reject the null hypothesis. So for example, if you look at knee circumference, the p-value is practically 1. And so that means it's almost sure that we fail to reject the null hypothesis, and that indeed that covariate really is not significant to the regression model. Now, what we're going to do is we're going to take out these covariates one at a time from highest p-value until lowest p-value until we get until the only covariates that are left are ones with a p-value below 0.05. One thing we have to be very careful of when we're doing this, though, we also have to keep our mind on this R-square adjusted or adjusted R-square. We don't want to damage that too much. Right now, we have 73.5% prediction power in our model. So our model right now, with all 13 covariates coupled in it, has the ability to account for 73 or 74% of the variation in our data. So we like that. That's very good. I think that's good by any standard, scientific or observational, whatever standard you're looking at. That is a pretty good R-square adjusted. So we really don't want to sacrifice that. Now, of course, we may have a little bit of movement. It may reduce a little bit. So you have to come up with a threshold, what you're not willing to let the R-square adjusted go below. Now, that is completely up to you, your class that you're taking, or the situation or the study or the research you're doing. So maybe, for example, you're doing some kind of study and you're told that you can't have an R-square adjusted below 0.6. Well, great, then that is what you don't want to see that R-square adjusted go below. So if you start removing covariates, even though they're above 0.05, and all of a sudden you get a huge hit to your R-square adjusted, because that's going to change as we remove covariates, then you probably took out a covariate that was really important to the prediction power of the equation. So you're going to want to have to stop at that point and say, okay, maybe I should stop pulling covariates out of the equation. So with that said, we're going to basically go in a circle or in a cycle. We're going to remove a covariate that's above 0.05 for the p-value. We're going to look at our R-square adjusted, decide what to do. If it's still good, we'll go ahead and do the same thing again. We remove a covariate, check the R-square adjusted, remove a covariate, check to the R-square adjusted. So until we get all of our covariates p-values there below 0.05, or we harm or hurt or have our R-square adjusted hit that threshold, that low end threshold that we don't want, okay? So let's start. And here's how you do it. So I usually like to keep my windows side by side so I can work in the fit model window and also look at my results windows as well. In JMP, when you run the regression equation over and over again, it will create more of these fit least squares windows. So you'll have to stack them on top of each other. So let's do it. So the first thing I do is I will remove knee circumference. And to get rid of that, you go to your fit model window and you simply double click on knee circumference, and that gets rid of it. So you just double click on the covariate that you want to remove. Then I click run and it opens a new window. So we're going to drag this over. We'll stack them on this side. Now let's take a look at our R-square adjusted. We actually improved it. It went from, let's see, 0.74, I believe, 0.735, and it went to 0.736. So it actually went up a little bit. So that's good, but we have no problem with that. Okay, so let's go on to the next one. I don't see anything down there. So here would be the next one. It looks like chest circumference is going to be next. It has a very high p-value, 0.9297. So we'll get rid of chest circumference. And we click run. We actually went up a little bit again in R-square adjusted. So we're actually not harming R-square adjusted at all. We're making it better. So we keep going. So it looks like the next one, and in case you probably may or may not remember that JMP colors p-values that are above 0.05 in black, and it colors p-values that are below 0.05 in red or orange. And so right now we're only still looking at 4 that are above 0.05. And again, though, those might change because of collinearity. So I'm going to now do the next highest one, which looks like it's going to be ankle circumference. So we'll get rid of ankle circumference and click run. And we're still at 0.738 for an R-square adjusted, so we have not budged. Now here's an example of collinearity. I wanted to show this to you. So if you remember, thigh circumference, if you look at your previous window right here, this was the third round we did. Thigh circumference was at 0.054, right? Now, as soon as I removed ankle circumference, look at what happened to thigh circumference. It actually dipped below 0.05. So that's an example of that happening. So again, don't be alarmed by it, but just know that it happens. Okay, it looks like the next one I want to get rid of is extended bicep circumference. So I'll click on that. Click run. And we're at 0.738, again, haven't budged. And now it looks like the next highest one is hip circumference. Now it looks like it might be one of our last ones. So let's try it out. Let's see if that does it. And click run. Now notice what it did. So it now exposed two others that now went above 0.05. Again, this is okay. This is what this process is like. My R-square adjusted is 0.737. It went down 0.1%. So I am not worried in the least. So I'm going to go ahead and do the next one. So it looks like the next highest is neck circumference. We're getting close. Click run. 734, we went down another couple tenths of a percent, but notice we haven't even moved a full percent yet. I mean, we're talking about tenths of percents of prediction power, so we're not really worried at all. Looks like thigh is currently the last one, so let's see if that happens. So we get rid of thigh and click run. Oh, and it looks like we're still at 731, so we're still at 73%. We haven't moved from 73% the whole time. So that put age out of control, and now we're going to have to get rid of that. Now, if the model you were building for your customer or for your boss or for whatever, your research that you're doing, required age to be one of the covariates in the model, sometimes you have requirements. You have constraints that you have to meet. So, for example, a person's age might be critical for other reasons. You would then just leave that in there. We don't have any rules in our example that we're doing, but I just wanted to let you know, age was an important covariate. If any of these covariates were really important and you need to leave them in, you can do that. But we're trying to get the most efficient covariate list while still having a high R-square value. So that's what we're doing. So I'm getting rid of age and click run. Okay, so it looks like we've been able to get all of the covariates that we have left below 0.05, and they're all quite below 0.05. They're very close to 0 in most cases. And notice our final R-square adjusted. We never went below 0.73 or 73%. So this model, even without the 9 covariates that we got rid of, still accounts for 73% of the variation in our data. So that's really great. It's still really, really important. Okay, so what we want to then be able to do is we say, okay, great, we have the most important covariates that we need. They're all below 0.05. The R-square adjusted is still very good. In fact, it's just almost identical to what we started with. And so now we're ready to at least interpret the regression model. So now we have an equation. And the way we interpret the coefficients for this equation in the regression model is using this estimates column. So all of these, you see where it says estimate at the bottom here, those are your coefficients for your regression model. So I have Microsoft Word open here. So let's just quickly type this out just so you can kind of see what this would look like. So basically, we're building a regular linear equation using these 4 covariates and the y-intercept. So we're going to say body fat, which is really our y. So maybe I'll say body fat, and I'll put y in parentheses, is equal to, and then you just basically go down the list of estimates as your coefficients. So it's negative point, and I'm going to round up to 2 decimal points here. So negative 0.3 weight, so negative 0.3 times weight. So you plug in weight and you multiply that times 0.3, negative 0.3, plus it looks like abdomen circumference is 0.995. So we'll just upgrade, or we will go ahead and round that to 1. So it's just plus abdomen. Okay. Plus 0.47 times forearm. Okay. Minus 1.51 times wrist. And don't forget your y-intercept. People forget their y-intercept all the time. So minus 34.85. Okay, let's make that a little bit smaller so you can see it all on one line, right? There we go. So that's the whole equation. Negative 0.3 times weight plus abdomen, which is really just multiplying it by 1, plus 0.47 forearm, minus 1.51 wrist, minus 34.85, which is the y-intercept. Okay, so now you have an equation. So if I gave you someone's weight, someone's abdomen circumference, their forearm circumference, and their wrist circumference, you could give me a body fat percentage that is pretty darn accurate. That is accurate, as far as our sample data went, up to 73%. So not a bad deal. Okay, so we have an equation. So that's step one. We went ahead, well, not step one, it's one of the steps. So we have the regression equation. Okay, now, as you remember from your reading or probably maybe prior work you've done with simple linear regression, there are other conditions we also have to satisfy to make this work. And one of them is the equal spread condition. And the equal spread condition says that we want to look at the residuals. So remember, there are residuals here, right? There's a difference between, so if I gave you my weight, my abdomen circumference, my forearm circumference, and my wrist circumference, and you plugged it into this equation, it would say my body fat's supposed to be some percent, right? It would give you a body fat, a y variable. Now, if I went ahead and got all these measurements actually taken, okay, I may have a different body fat percentage. It's probably going to be off a little bit, right? Because models don't work all the time. In fact, this one only worked 73% of the time when it was compared to our data. So the residual is the difference between what the equation says, which we call the expected, and the actual, which we call the observed. So we want to look at those residuals plotted against all of the expected values. So that's what we want to see, okay? So we want to plot them, and we want to determine using that plot if the plot of the residuals looks what we call equally spread. All right, so let's do that, and I'll show you what you're looking for. I'm going to minimize our equation for a moment. So on your last window, whichever one you arrived at last, so in this case it was fit least squares 9. JMP does number them, by the way, so you can look at which one was your last one. So on your last window, you go to your red hot spot at the top of the screen, go to row diagnostics, and then click plot residual by predicted. That's what you want to do. And if I scroll down, that will give me my equal spread plot. Now it's really just a scatter plot if you haven't noticed. So on the x-axis is the body fat percent predicted. So that's what the model is actually saying, the linear regression model that we came up with, that was in my Word document. That's what the model says. So we plugged in, what it did is it took all of the values in my data set, plugged those values into the model, got an expected, and then compared that to what the actual one was, which is the one that was in my Y column, and it got the residual. So notice in the middle, down in the middle, this blue dotted line means there's no residual, and on either side there's positive and negative residuals. So what are you looking for? You're looking for this particular plot to be what we call uninteresting, which means the dots are kind of all over the place. And in our example, they certainly are. The dots are just everywhere. There's really no pattern, no rhyme, no reason. They're kind of just everywhere, and that's what you want. So that means that the model, yeah, it's not perfect, but it looks like it's not perfect uniformly or consistently across all values of body fat percents, all the way from, it looks like from 5 all the way to about almost 50. It's just kind of off in all directions. Now, what if yours had a pattern? What if, for example, you had small amounts of residuals really close to the blue dotted line for body fats under 20, but then maybe all of a sudden your residuals exploded out towards the edges of the plot for things larger than that? Well, does that mean that your multiple regression was a complete failure? Of course not. What that means is this particular regression equation happens to just be better at predicting values of body fat below 20%. And that's okay. You would have to state that in a report when you're reporting to your boss, or when you're writing up your research report or your lab report. You would just have to state that it did not pass this particular condition, the condition of equal spread. And you would say the equal spread condition was violated, and here's why. And you could say, look, anything less than 20, it seems to be good, but anything more than 20, the residuals go up. And that might not matter to someone, but you should definitely report it. Okay. The next thing we want to do is we want to graph the residuals all by themselves, not against anything. We want to graph the residuals all by themselves and take a look at what the distribution looks like. And the distribution of the residuals should be what we call nearly normal, and you should know that condition by now from past tests. So we want to make sure our values of our residuals look nearly normal. So in order to do that, we have to graph our residuals. So to do that, go back up to your red hot spot on the same window, and you're going to go to Save Columns. And then you're going to click Residuals. Okay, that's what you're going to click. So go to Save Columns in Residuals, and it's going to look like the system did nothing, but it did. If I go back to my data set, you will notice it created a new column in my data set called Residuals of Body Fat Percentages. That is my residuals. For every line, there's a residual between what the model said I should have for body fat percent and what I actually had for body fat percent. So now we can just graph that. So we're going to graph that single variable. We'll go to Analyze Distribution and drag residual body fat percent into the Y column and click OK. And I don't know about you, but that looks pretty darn nearly normal to me, especially since it's such a large sample size. It's 252. Our requirements or our, how strict we are in interpreting whether something is nearly normal drops when we have large sample sizes. So even with a large sample size, this is really good. This is a nearly normal. So it passes the nearly normal condition, and our residuals look normal. Okay. There's one last thing that we should do before we finish this, and that is to perform an F-test. And what an F-test determines is whether or not the regression model you've just created is better or worse than using the means to predict future values of y. Now, we learned many times ago, or you've probably learned many times, that a mean is a very nice measure of center. It is a good way of kind of giving an average of a particular value. So they're really good at almost kind of predicting. So is that better than coming up with this really great regression equation that we worked really hard on? So the F-test is really a hypothesis test with a null and alternative hypothesis, because if it's a hypothesis test, it has to have one. And the F-test is, the null hypothesis is that the regression equation is no better than using the mean. Okay, that is the null hypothesis for the F-test. The regression equation that we just built, that equation right here, the regression equation is no better than using the mean. And of course, the alternative is that the regression equation is better than using the mean. So we just need a p-value for that, and we've solved it, correct? So it just so happens on your last output window, again, that number 9, if I can get it back up on my screen. Let's see. Yep, here's 9. So on our last window here, number 9, if you look in the analysis of variance section, right in the middle, you will notice in the lower right-hand corner, there's this probability greater than F. This is your F statistic. So this is the p-value for that F-test. And as you see, it's certainly very low, and it's definitely lower than 0.05. So that means I reject the null hypothesis that the regression equation is no better than using the mean. So that way, we're good to go. We are definitely in good shape. This was a good regression equation. It was not a waste of time. So now I can use this equation that I just came up with, or that we came up with together, to predict values of body fat. And it's much better than using 13 different covariates. All I have to do is get someone's weight, their abdomen circumference, their forearm, and wrist circumference, and that's it. And within 73% of certainty, I can predict for body fat percent. So that seems to be it. If you have any questions, please post them in the comments, or you can ask me in class if I'm your professor. Okay, have a great time, and I hope you enjoyed.